Okay, I think that we can start. It's a pleasure for me to introduce the first speaker of this section, Professor Hakim Monaim from Moulay Ismail University, Meknes of Morocco. His talk is titled Wigner-Ville distribution associated with the quadratic Clifford-Fourier transform. Thank you very much.
Thank you very much, Professor Maria. In 1946, Denis Gabor used translation and modulation of the quotient signal to introduce its time frequency representation for signals. But this structure of translation and modulation to extend to other abelian groups. But in physics, there is many of groups that there are no abelians, such that Heisenberg group. So the STFT theory abelians fails. This fact persists us to generalize this short time Fourier transform theory for no abelian groups. This presentation will follow the following plans: some preliminaries, algebra of quaternions, and the spherical functions on the unit ball. And the second section is to Helgason Fourier transform and give the entropy uncertainty principle. The third, the time frequency analysis, so the Gabor analysis on the unit ball. And we will give the characterization range and the Lieb uncertainty principle. So the algebra of quaternions H is a four-dimensional non-commutative associative and division algebra, which one AGK obeys the following rules. Every quaternions can be split as a real and imaginary parts as follow. A of x is x0 and the rest part is the imaginary part. Every quaternion we define the conjugate as follow, and the modulus, the square root of the sum of square of components. And we can get immediately these properties. The conjugate of the product is the inverse of the product of conjugates. You can find all these details in this paper of Hamilton. So now we define the n copies of H, and this space is with the Hermitian product AB is equal to the sum of AK, BK conjugates, where A1 to AN and B1 to BN are in HN. We denote by SP1 the subgroup collecting the unit quaternion, which is isomorphic to SO3 group. And GL in H is the group of non-degenerate matrices with entries in H. SPN is the group of matrices in GL in H which stabilize these Hermitian forms. And the SPN1 is the subgroup of GLN plus 1H which leave invariant these Hermitian forms. AB with brackets is equal this sum, but the last one with minus, which equal this Hermitian form minus AN plus 1, BN plus 1 conjugates. The last notation is PN product SP1 is defined with the group of A Q, where I is a an element of SPN, and Q is in SP1. First proposition, which we find in Jacques Faro, if we donate G is SPN1 and K is SPN products SP1, then JK is a symmetric pair of rank 1. The homogeneous space G, called the quadratic hyperbolic space, is doubly transitive Riemannian manifold. So, JK is a Gelfand pair. The quaternionic hyperbolic space of maximal sectional curvature -1 is isometric to the unit ball. So, our work will be on the unit ball, which is isomorphic to the hyperbolic space. A smooth function phi in the unit ball is called spherical function if it obeys of these properties. It is K-invariant, and phi of 0 is 1, and every derivative on the unit ball, there exists a lambda d in C such that phi is a eigenvector of the on the unit ball, denoted by G invariant differential operator in the unit ball Bn. For every lambda in C and Z in unit ball, and S in the Sn, the complex power of Poisson kernel is defined by P lambda Z is S is this value. This definition is in this book. The second proposition, for any vector in the unit ball and Z on the unit ball bar, we have this equality. For each FC to unit ball to complex space, the space of complex values C square function, we have LF of A is equal nabla of F sigma A of 0. The operator L is the Laplace Beltrami on the unit ball, and delta is the Laplacian operator. Sigma A is an involution isometry of the unit ball. Again, you can see Jacques Faro, analyse harmonique sur les paires de Gelfand et les espaces hyperboliques. A spherical function on unit ball. The function P lambda ZS is an eigenfunction of the Laplace Beltrami operator with eigenvalue, this value. A spherical function on Pn have the form, if you integral on Sn, this function, where Ts is the invariant Borel measure on the sphere Sn, with sigma of Sn is 1. There is some remark. We can show the spherical function phi lambda is positive definite in the following case if lambda is IR, where R is a real, or lambda in the real axis between these two values, or lambda is equal plus minus to n minus 2, and phi lambda is equal phi minus lambda is equal 1. The spherical function phi lambda is bounded if only if the real part of lambda is between these two values. Now we have the ability to define the L-Gazon Fourier transform. Some notation: dPn is the space of smooth function or with a compact support. And the natural Bn is the space of radial smooth function with compact support, and this space is the space of radial square integrable function on the unit ball. For any function on this space, we define the Hilgazon Fourier transform by f of lambda s is the integral on the unit ball if z p minus lambda zs d mu z. For radial function, the integral, this transformation becomes in this form. First theorem, we can recover our preliminary signal if z by this formula. The 1 over half, we integrate up on the real axis the sphere and this value. You can find this result in Hilgazon groups and geometric analysis. Now we have to use the Hausdorff-Young inequality for this transform. For P between 1 and 2 and Q, it's the conjugate, we have this inequality. And we get immediately the definition of Rayleigh and Channel entropy. The Rayleigh entropy of F on a space X with the measure Dx is given by HR of F is 1 over 1 minus R logarithm of the integral of X to the R of X dx, where R is different to 1. When R goes to 1, the following Channel entropy is equal H of F is equal minus the integral of X, Fx, logarithm of Fx dx. This is one of our results. If F is in the LP, the unit ball by the measure d mu z, and P between 1 and 2, and Q is the conjugate, then we have this inequality, HP over 2 of F square and HQ over 2 of psi phi to the 4, where phi is defined by this integral. Now I have to go to the Gabor transform. Let's fix a window psi different to 0 called a window function. The short time Fourier transform of f with respect to psi is defined by g psi of f z lambda s is equal this integral. Always d mu omega is the measure which we defined earlier. For z in the unit ball and lambda s in the unit ball hat, and p lambda is given by 7. The following identities are easy to prove. For example, for z in the unit ball and lambda s in the unit ball hat, we have g psi of f is equal f z psi hat. And this is easy to prove. Some forward calculation. Now we have a proposition. Let's psi a window function such that psi is a square integrable in the unit ball. Then for each f square integrable, for each signal square integrable, we have this identity. So the norm, the L2 norm of G psi f is equal to L2 norm of f multiplied by L2 norm of psi. This is the similar formula of Parseval. Now I will define the characterization of the range of short time Fourier transform of Gabor transform. We define the W psi L square by the signal, which can be written as G psi of G, where G is a square integrable signal. So if we take a square integrable signal on the unit ball and the square integrable window such that the L2 norm is equal 1 of the window, then we have f is in this space if only and if it satisfies this equation. We try to resolve this equation to get the exact form of f, but we can't. Now I will go to Lieb uncertainty principle. Let epsilon greater than 0 and omega measurable part of x, a function, a square integrable function on x is said to be epsilon concentrated on omega if the integral outside of omega of f squared is less than epsilon of the LT norm of f, where omega c is the complementary of omega. We have the first lemma of Lieb inequality for p between 1 and 2 and psi a window function on LP and L2 on the unit ball, and f a signal in LP and L2 such that p is the conjugate of p, then we have this inequality. We can control the integral of g psi of f by these two norms. Now we have the Lieb uncertainty principle. If we take a window function psi, a square integrable window function and square integrable signal such that if no node for epsilon positive and omega in unit ball times the real axis is a measurable seat. If g psi if f is epsilon concentrated on omega, then every Q we can get this inequality. The measure of omega is greater than 2 times 1 minus epsilon square to the q over q minus 2. Here's some our references. This is Feichtanger and Helgason, Radon Fourier transform on symmetric space and related group representation. And we have Denis Gabor, Theory of Communication, Part 1. And thank you very much.
I thank you.